writing on the bin.
Hello, Mr. and Mr. Ryan. How are you today? Good?
Good.
Okay. Okay, so remember we talked about graph recently, okay? What's graph?
A graph is a graph, which is a graph, which is a graph, is a tree.
Tree is also a graph, but yeah, data structure, and we can use it as a G to represent a graph.
Like DIG.
And what component does it have, the graph?
DIG.
Vertex and edges.
Vertex and edges. V for vertex and E for edges. Okay, and it can have all these directional graph.
DIG.
DIG, directional acyclic graph, which doesn't have the cycles, and directly means that the from A to B, but not essentially from B to A. Okay, so that's
And not essentially.
yeah. Let's talk about this directed graph. Okay, so given the directed graph, okay, like look, 1, and then 2, 3, okay, and then I have at least 4, and then this have 5, and 6, okay.
Yeah.
So this is directed graph, and okay, so we can have this weight, you know, the weight, W-E-I-G-S-T, weight, associated for weight is the associated for
If
this
you read
weight.
that line from 4 to 6 to the line, not 3 to 5, it'll make a pentagon.
Okay, okay. So what's weight? Weight is like I can have different weights for each ages. I can label the cost, for example, like this 3, 4, and then it's 5, 2, 1. Okay. So what does it mean? It means that from 1 to 2, it takes 3 seconds from 1 to 2, right?
Yeah.
Maybe 3 seconds or 3. You know, it costs 3 units or
What
something.
do you mean cost?
Because of the weight.
No money.
Look.
Something like that. Okay, for example, like you, Eric, you are here, right?
Yeah.
You want to go to travel from 1 to 2. You need to cost 3
I'm a
pounds.
conductor.
2 to 4 pounds, for example, or 3
I don't-
seconds, 4 seconds. Can you listen to me, Ryan?
I want to say seconds.
Okay, second. 1 to 5.
Just wasting
1 to
my
4.
money.
Okay, 1 to 4, 5 seconds, and 4 to 2, 4 to 5, 2 seconds, right?
Okay,
4 to 6, 1 second. Okay, so you can look at this number above the edges is called weight. Okay, you can in real world it can mean something
Is that
like
a tree?
good point. Yeah, it's a tree. Yeah, tree is kind of the DAG, right? And we are talking about a graph here. Yeah, tree is kind of graph. Okay, DAG.
That is a tree.
DAG. Okay,
It
DAG.
doesn't look like a tree.
It's a tree,
It
like
doesn't
root,
have-
left, right,
It
right.
doesn't
Yeah.
have a
Binary
branch.
tree.
It
Okay.
doesn't have a branch or trunk or leaves.
Tree. This is the root. Yeah. Okay.
Oh, we don't.
Yeah. Okay. Let's talk about. Look, Eric.
Yeah. I got.
But the tree doesn't have. I got it. Look, I got it. The tree doesn't have a weight for above each edges. This is the difference. Yeah. The graph has the edges. Okay. So the question is here. The question. Now we talk about the question. Eric, come on. Given a star, right? Like 1. Given a star equals 1. Okay. We want to find out the maximum time for 1 to deliver all the, to travel all the to all the nodes. Right?
Yeah.
Alright, Ryan, can you listen to me? Don't play with that, okay? You're on video, okay? Come on. Yeah?
Yeah.
So, in this case, what's the answer? Look, 1, we want to find out the distance between the shortest distance, yeah? So, the shortest distance. For example, if I have another one, 1, 2, 3, that's 100. Okay?
That's impossible.
No. I'm talking
It
about
takes
if.
100 seconds.
Yeah. Okay. So So what's the shortest distance between 1 to 3?
Go 3, 4.
Where
It's
that goes 3, 4.
impossible.
This 7 is much faster than 100. No. It's possible in real world. I mean, for example, if there are lots of the traffic in this road, right? Yeah. Yeah, and then the GPS, the navigator tell us that it's better to travel the other road, which is faster because there are less traffic. Yeah. Got it? Okay. So the question is
How
that.
can there be a million traffics on
No.
one
I'm
road
just an example,
and
okay?
no traffic
Listen.
on the other roads?
Listen up. 1. So we want to find out the maximum unit. Okay. So the first question is that we want to find out the shortest distance between 1 to each node. Okay. Yeah. Or any nodes. For example, like 4 to 5 is 2. And then if I can have another one here, like 7 here, if this is 0, and this is 0.
It
What's
takes no time.
Oh, 0.5, 0.5. It takes how much? What's the distance between 4
Yeah.
And 0.5 and the 0.5.
Yeah, exactly.
0.
Okay, so in the given the DAG a graph,
Yeah.
we want to find out the shortest distance between any two. Okay, we want to find out the shortest distance between any two nodes, vertex. So today we'll talk about this problem, right? Yeah? Because this is important to know that if I want to give it a start, I want to find out the maximum unit to travel all the nodes to, from 1, right? Yeah? And then we can visualize it as the shortest distance between 1 to every other nodes. Yeah, and then we find the maximum, right? And sometimes, look, if 1 doesn't reach 7, maybe 10 here, right?
There's no 10.
I know, but there's no path between 1 to 10, right? So we return to -1, okay, in this case. Okay?
10 is on its own.
So, yeah, 10 is on its own. What's the, you mentioned, you understand this, yeah? If a node 1 travel to 2, right? We know this cost 1. And if 1 travels to any other node, let's n. Yeah, if this is C2 and this is C3, right? If C1 is smaller, if C2 plus C3 is smaller than C1, right? Yeah, then we update the cost from 1 to 2 with this update, yeah? Because this is faster, right?
Yeah, but in real life, that C1 thing has...
No, because we have a weight. You can consider it as the time, the cost. Got it? It's not the, it's not the geography distance. It's the cost with the cost. Okay? So we want to find out. Basically, today's task is that we want to find out the shortest distance between any two nodes. Okay? So how can we do it? Based on this, if we update it, if we iterate all the nodes, right? All the pairs. If we iterate all the pairs and we update the shortest path, right? This is we update the shortest path. If we find a replacement. Why this is working, Eric? Look, okay. Why this is working? I explain to you. Okay, can you listen to me? Look, if this is the path, right? This is the path A to B. And then here will be C. Okay, so if there's another path here, if there's D and then let's E. Okay, let's E.
I'm there at the end.
I'm there. I don't know where.
Okay. Okay, so we want to find out the shortest distance between D to E. Okay, if this is like 100, this is 10, this is 20. Okay. Yeah.
How about the D to A and B to E?
D to A. No. Okay, this may be 1. This is 1. Okay. So look, we can find out. We can always replace because A to B it cost the ultimate is from 10 plus 20 instead of 100, right? So we can always replace the overall path D to E with this bit. Yeah. So the ultimate path will be DA, AC, CB, BE, right? It's much better than DA, AB, BE, am I right? Yeah? Yeah, if I replace it with this. And if later I found out if there's another path called G, which is 5, 5. And then I can update the whole path with this one, right? Yeah, with this one, yeah. 1 DA, A, G, GB, BE, you see? So we keep updating this until we found the shortest path between D to E. Got it? Yeah? So if there are n node vertex, yeah, we're talking about today, we want to find out the shortest distance between any two vertex in a graph. Yeah, in a graph. Okay, so the extension, if we, okay, let's do this. Okay, define shortest distance. Okay, shortest distance. That's a graph. Okay, and then we have n. N is the number of vertex. Okay. So first of all, we want to have a distance function. Yeah? Distance array. Distance. If we use the distance, a two-dimensional array AB, what does this mean? Means the shortest distance between A to B. The vertex A to vertex B. Okay, we use this one. This is the two-dimensional, right? Two-dimensional. A list of lists, right? So how can we do this? At the beginning, we initialize this to what's the biggest number you can think?
Infinity.
Infinity. Okay, so look, it will be math dot infinity for
Well, we're not doing maths, we?
range n,
We're
right?
doing program.
This is the list, and then for in range n, yeah, this is a range n. So this is this gives the distance two-dimensional array, which we can visualize it as, look, distance 1 1. What does it mean? 1 2. Okay, so it's the vertex 1 to vertex 2. The distance, the short distance. Okay, so can you tell me that if what's the value of this like 0 0? What should I give it? Like 1 1. So this AA. What should we assign the values to it? No, the shortest distance between the node to itself. Okay, so 0 to 1. Okay, 0 to 1, this is 1. Okay, and what's the distance between 0 to 0? Come on, what's the value? What's the value that we should give initialize to 0 to 1 1? Yeah, 0 to 0. Yeah, because it costs nothing to. You're already there. Yeah, it costs 0. We're done. So what should we do? For I in range n, right? Yeah, and then what should we do? Dist I equals what? Dist I equals what? Come on, dist I equals what?
This.
Come on, this I from the distance between I to the vertex I to vertex I. You just said it before. 0. Okay. Okay, so this
Look how.
this matrix, okay, this matrix will be something like that. If there, look, Eric.
Yeah.
If there is a distance two-dimensional array, if n is like 4, let's do it as 4, okay? If n equals 4, so this is give a metric what? Can you feel that metric?
4.
This I, so this diagonal will be 0, right?
Yeah.
And what's other values? What's other values?
4.
4? What's the other values? Come on. What's the other value initialized to?
1.
Where's 1? What do you mean?
4.
4.
There's 4.
No, n equals 4, so this is 4 times 4 metric.
Oh.
And I is 0. And what's others value? Come on.
Infinity.
Infinity, yeah. So all these values are infinity, yeah. Very big, okay. You know how to represent the infinity in mathematics? In mathematics, you know how to represent the infinity? What's the symbol?
That.
Yeah. Look, number A but horizontal. This is infinity, yeah? Ryan, yeah? If you look it that way, it's A, but if you put it horizontal, this means infinity. And beyond, okay? Infinity. The largest number, okay, is infinity, okay?
Infinity.
Okay.
Plus infinity.
Okay, so we have this the metric, right? So this I to I, for example, what's this value mean? What's this value mean?
Times.
No. What's this value? If this is okay, if this is 1, what does it mean? If this is 1, what does it mean? The second row, first column. So how do we represent in here? Is this 0 1 0? So what does it mean? This value, what does it mean? The distance between which two nodes are 1. Come on. The distance between 1 and 0 is 1, right?
1.
Got it? Do you understand now? Yeah? This is what I mean. Okay, another one. What's the, if this is 2, what does it mean? This 0 1. And what's this? 0 1 2. What does it mean? If this is 2, what does it mean?
1.
If this is 2, what does it mean? What do you mean 1? The distance between which two nodes?
1 and 2.
1 and 2. That's it, yeah. So distance AB means that the shortest distance between A to B is here, right? Got it? That's what it means. Okay, so now, given this, so what else? We just need to do this for K in range N. Okay, so another for I in range N. This is easy to understand later, okay? And then another for J in range N. So what's the time complexity if we write the three loops? What's the time complexity if we write the three loops? Three loops, yes, four loops. What's the time complexity?
3.
Sorry? Over. This is n, this is n, this is O(n)(3), yeah? O(n)
I
cubic.
said that.
Okay, O(n) cubic, okay. Okay, so we given this graph, okay, but we haven't, this graph is the given this age, yeah, from it will be A to B, and then weight, okay. So first of all, we need to update this, okay. So I write here, we forgot here. Here, okay, we forgot here. Is that for A, B weight in G, for A, B weight in G, and then we update this distance. A, B equals weight, okay? Yeah? This is the to handling the input array. G for A, B, from the vertex A to vertex B costs W, right? So we put it in this metric, yeah? We put it in this metric, A to B, W. Okay, so now, look, if the node, okay, this is I node, yeah, this is I node, and this is J node, right? What's the distance between, what's the current distance between I to J? How can we represent it? Alright, how can we represent it? How can we represent it? Alright, Ryan, come on, what's the distance between I to J? How can we use it? This I to J, what's that?
I to J.
Yeah, come on. This is easy. This Ij will be the minimum of what? If we found another one, this I to J, okay, we write it here. But if we found this K here, yeah, this is K here. If we found what's the distance between for I to K and K to J? Come on. We know the I to J, current I to J is this Ij, right? Yeah? What's the distance between I to K? This Ik, right? What's the distance between K to J?
K to J.
Yeah, this Kj. So how can I write this? If this Ij is, look, if this Ik, wait, look, if this Ik plus this Kj, come on, is smaller than which part?
I J.
Yeah, if this bit plus this bit is smaller than this bit, so we update this bit to this bit plus this bit. Got it? Yeah? So we can write using the mean. So what should I put here? Is this the what? Ik plus this what? K what?
I.
No. I to J, if it's bigger than I to K and plus K to J, so
J.
J, yeah, that's it. So look, we use the mean function, but it's the same as, look, this is the same as what? If this Ik plus this Kj is smaller than this Ij, what does it mean? It means that we can use this path to replace the path between I to J, right? That's exactly what it means, okay? And the distance between, if we given a star, yeah, the distance between, after this, the shortest distance between 0 to all other nodes will be in this this 0. Okay, that's it. 0, 1, 0, 2, 0. Oh, okay. What's the time complexity for this one? Have we mentioned? Oh, and what's the time complexity? Oh, and cubic. Okay. What's the space complexity? Oh, are we using any space? Oh, are we using any space? What's this? Huh? This is two-dimensional. How many? If n is 4 nodes, how many? Remember we talk about this. We have this. What's the this space? If n is 4, you have the how many?
1.
I'm using any space. Come on. What's if n is 4? How many units are there? How many?
16.
So what's that?
It's n squared.
Oh, n squared. Come on. Yeah, n squared. Got it? Yeah? Okay, I'm going to erase this bit, okay?
Why?
That's it. And I'm going to do this. N. Yeah, this is all, okay? So what's this? So this is I to J. We want to update I to J, but now it's a K. If there's a path, I to K. I to K, K to J. Okay, so can you tell me what to write? Eric, can you tell me what to write? Come on, can you tell me what to write? This one. Huh? What? No, there are 4. What's this here? I want to update I to J. So this IJ equals what?
This.
We want to find the minimum of these, yeah? So minimum of this IJ, yeah? We want to keep updating the value. And then what path should we compare to? IJ, what path should we compare to? What path should we compare? What path compare to? I to
K.
plus what?
K to J.
Yeah, so it's this IK plus this what? K to what?
J.
Yeah, well done. That's it. Good job today. Okay? Got it? So this is the shortest path, okay? And then if we want to find the maximum from, we have a star here, okay? S here. Then we can return what? Maximum G this star, okay? Star. Okay. If this is not -1, okay? If this is not max infinity. If it's max infinity, what does it mean? It means, what does it mean if the value in this IJ is infinity? What does it mean? Everybody? After this program, if it's still the value is still max dot infinity, what does it mean? What does it mean? Come on, what does it mean if it's, the value is max dot infinity?
It means that.
Like what? Come on, I mentioned this at the beginning. If the value is still max dot infinity, what does it mean?
It means that
Is there a path between? There's no path, right? If there's no path, then the value will be still max dot infinity. Because if there's a path, right, anything compares to max dot infinity will be updated, right? Right? If it's not updated, because the value at the beginning, yeah, except this diagonal, all other values are max dot infinity. If this value is not updated, what does it mean? There is no path between that two vertex, right? It will separate, right? So it will not be updated. So at last it will be the max dot infinity. Okay? Okay, that's it for today. Good job. Say bye bye.